The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and welcome to the 2021 Virtual Viscosity Summit. We are going to get started with our final session of the day in just 1 minute. We're going to give everyone just one more minute to go ahead and log on, and then we will go ahead and get started. Good afternoon, everyone. My name is Eden Reed, and I am the Senior Marketing Associate for RheoSense. For those just joining us, I would like to welcome you all to the 2021 Virtual Viscosity Summit. Before I introduce our next speaker, I'd like to go through a few housekeeping items for our final session. We would love to connect with you on social media. Please follow RheoSense on LinkedIn, Facebook, and Twitter to stay up to date with all the latest news and viscosity discoveries and updates. Now, each of our speakers today has left time at the end of their presentation to answer questions. So we encourage you to ask your questions in the chat pane throughout the presentation, and our final speaker will be answering them at the end of the presentation. And finally, we have a reminder that all our presentations today are being recorded, and the recordings will be sent out to all registrants 1 week after the event concludes. Before I introduce our final speaker of the day, I would like to let everyone know if you are attending Pep Talk this week, Dr. Stacy Elliott, our principal scientist, will be presenting tomorrow morning. That's the 21st of January at 9:50 a.m. So please go ahead and tune in to her talk. And now, without further ado, it is my pleasure to introduce our final speaker of the day, Dr. Zachary Imam. Dr. Imam obtained his PhD in biomedical engineering from the University of Texas at Austin and spent a year postdoctoral continuing development on a bioscience project funded by the Department of Energy's Basic Energy Science program, studying the biophysical properties and functions of microtubules. Today, he will be presenting Optimizing Formulation Development, Understanding Viscosity's Role in the Formulation Process, and How to Create a Measurement Plan. So now, it's my pleasure to turn it over to you, Dr. Imam.
All right, thank you for the introduction, Eden. I hope everyone can see my screen. So again, good afternoon, and thank you for attending our first ever Viscosity Summit. And thank you to all the speakers who shared their work today. They were all really great and wonderful presentations, and definitely learned a lot. So today I'll be wrapping things up by discussing viscosity's role in formulation development and how you can use rheology, specifically viscosity measurements, to develop your own measurement plans. And so viscosity and rheology in general is exploratory and iterative. So unless you're doing quality control experiments on something that you've heavily characterized, you're not going to be able to predict rheological behavior in your formulation changes. So we like to illustrate this in this flow chart where we have our formulation, that's our excipients, maybe the temperature it's operating under, or buffering agents, or just buffer in general. So here we have xanthan gum, which is a common thickener in the food industry, as well as the cosmetics industry. We have the structure of arginine and histidine, two amino acids that are also used as viscosity reducers in biopharmaceutical applications. And then we also have here a poloxamer, which is a tri-block copolymer that's being investigated in also the drug delivery field, as well as our friends sodium and chloride, which are a common buffering agent in many formulations. And so each of these excipients has an impact on the interactions and microstructure within the formulation, within the active components, and sometimes not even the active components of your formulation. And these interactions and changes in the microstructure are then reflected in viscosity measurement. Changing the formulation can dramatically change the viscosity and also the rheological behavior of your formulation over a wide range of shear rates. And it also can change the temperature behavior as well. And just because you can't predict it doesn't mean you should be afraid of taking viscosity measurements. You just jump in, tweak your formulation, and see what happens. Personally, that's what makes rheology fun to tinkerers such as myself. You can change one aspect of the formulation and see how that changes the viscosity later, and see if that can guide you towards an improved formulation. And so with that, I'll briefly go over what viscosity actually is, even though multiple speakers today have already gone over viscosity. So in the simplest terms, viscosity is a fluid's resistance to flow. And so here we have an example of a simple flow field induced by a parallel plate type viscometer, where as you have a stationary bottom plate and then a top plate that's rotating. And as you increase the height towards the moving plate, the velocity of material increases to velocity max at the wall of this moving plate, and the velocity min at the stationary plate down here. And then as you go up, you then get this velocity gradient, which is perpendicular to the direction of flow. So you start at zero velocity here all the way to max velocity here. And it's a shearing motion that causes the adjacent fluid and the elements to slide past each other. And you can also think of this relationship of shear stress induced by flow and shear rate, which is the rate at which the shear is changing on this perpendicular axis, as the viscosity eta. And this shear stress and eta are dependent, or eta is dependent upon temperature, shear rate, concentration, and even time. And so we can think of the shear viscosity as internal or molecular friction. And these changes are indicative of the microstructure and size and shape of your components. And so how can viscosity help you? Well, in a practical sense, you can calculate or contextualize the injectability of your formulations if you're injecting antibodies into a patient. You can also, as Shear mentioned in the previous talk, that you can improve your processing. Other industries, such as the contact lens industry or just eye drop industry in general, is focused on blinking. And then the cosmetics industry is concerned with topical applications of their products. And then everyone is worried about aging and aggregation and all sorts of other things. And we can use the viscosity to kind of predict the performance and processability of our formulations. And remember, it's an investigative tool. Viscosity reflects the microscopic behavior. It would be great if we could shrink ourselves down into microscopic level and observe what happens to our formulations at that level in person, but we can't do that. So one way we can do that is to measure viscosity, which directly reflects what's going on at that submicron level, the size and shape of our individual molecules, the pair interactions between them, any complex structure formation, in solution, the impact of the solution on the environment of all of the above. And one last thing is be flexible. You may have a preconceived notion on what your viscosity is going to look like, your target viscosity. But what we need to do is have intelligent formulation, work smart, not hard. Don't try and force something that's impossible to make. Just make your formulation, test it, see what it looks like at that base level, and then start tweaking it and build more complexity, and then go towards whatever goals you may have for that specific formulation. And so with that, I'll briefly summarize how our technology at RheoSense works. VROC technology, viscometer, rheometer on a chip. It's microfluidics and MEMS based. So we have MEMS sensors in our flow channel at 4 different points, and we control the shear rate or flow rate in our instruments, and then measure how the change in shear rate, flow rate changes the drop in pressure across this channel. And then we correlate this drop in pressure to the shear stress. So we control shear rate and measure shear stress, and then we divide the measured shear stress by the controlled shear rate to get a dynamic viscosity measurement. And now if you're interested in kinematic viscosity, all you need to know is your solution's density, and you just divide your dynamic viscosity by density to get your kinematic viscosity. And then one more thing on how our system works in particular. There's no air-water interface in here, so there's no air-water effects when working with our instruments. So, and with proteins in particular, we're worried about aggregation at the air-water interface, and that's not really an issue in our system. So with all that summarized, how do we start a measurement plan? And so before you do anything else, before you jump in, you need to ask yourself, well, what do I want to learn about my sample? Will my study be narrow and specific, or will I be performing a broad characterization study? Am I worried about how my formulation performs in a high shear environment or a low shear environment? Do I worry about what it's going to behave like at high temperature or at low temperature? Or am I trying to understand what my fluid structure is, or maybe even the molecular structure? Or am I trying to differentiate between several different formulations and trying to pick out which one meets my goals more closely? And so knowing this information beforehand will help you create a great measurement plan and also help you design better experiments. And so start things off to check on performance at high and low shear rate. Now, my method, and I noticed specifically with Sham Shear and Carl Afton's process, they do what I like to do, which is to start broadly and then narrow things down. So what I like to do is to start broad on a shear rate sweep, and then pick specific shear rates that are applicable to my specific application later. Because the more, viscosity isn't just one number. It can change at different shear rates. And there's usually, once you've done a shear rate sweep, you can predict kind of how your material is going to perform at different shear rates. And so you get a better understanding of how your formulation is going to work. And so then once you have this general knowledge, you can get really specific. So that's my approach. So here on the left, we have a high concentration protein in 2 different PBS buffers, one that contains arginine hydrochloride and one that does not. And so arginine is a excipient known to reduce viscosity, and both Amjad and Dr. Johnston and also Bart Deer mentioned the details of arginine hydrochloride in much more detail than I'm going to go through today. And then on the right here, we have some xanthan gum formulations which behave in the power law. They're power law fluids, which are very similar to the types of fluids that Dr. Afton works on and presented on earlier today. So these have dramatically different behavior And what's, at least to me, really, really interesting is we're in the same shear rate range. We're at 1,000 inverse seconds here, and 100,000 inverse seconds over here, 1,000 inverse seconds here, and then 100,000 inverse seconds here. But we have dramatically different behavior. And the reason why we have dramatically different behavior is that the individual molecules inside our formulations, as well as the formulations themselves, are dramatically different. So over here, we have a globular protein that is about 150,000 Daltons, and these are inherently attractive colloidal particles in solution. So at low shear rates, they're going to be diffusing around, and where they're going to be interacting strongly. And then it takes a large shear stress to disrupt that diffusion, that Brownian motion, to then induce them to shear thin. Whereas the xanthan gum is a millions of Daltons polymer. It creates an entangled polymer network that it doesn't take much shearing to induce a conformational change and get them flowing all in one direction, which reduces the viscosity. So as you can see over this shear rate range, we have dramatic behavior, but we also, with just changes in this case, excipient, or in this case, percentage of polymer, we have dramatic changes in viscosity as well. So it's all interconnected. And so to go further into analyzing our viscosity data and trying to understand how this can guide our formulation process and create a measurement plan, we need to define a few parameters. So this is the standard curve for viscoelastic fluids, and I think just about every talk today had some image that was similar to this. Where over here at low shear rate, we have what's known as the zero shear plateau or the Newtonian plateau. Note that zero shear doesn't mean zero shear rate, a shear rate of 0. You can't measure viscosity without shearing a fluid. And so if you look over here, we're shearing at 1,000 inverse seconds on this data, and we're still on the zero shear plateau. So I just wanted to, that term leads to a lot of confusion because in most instances, 0 means no movement, but not in the case of viscosity. And so here at the zero shear plateau, the thermodynamics of your system dominate. But then once you shear at a high enough rate, you'll then induce behavior known as shear thinning and enter the power law regime of your fluid, which is what we can observe clearly with the xanthan gum that I showed on the previous slide, and in Carl's polymers that he works with. We're in the power law regime there. And this onset is denoted by the critical shear rate, which is just the shear rate where we start observing shear thinning, which is non-Newtonian behavior. So the zero shear plateau is also called the Newtonian plateau because that is where we see viscosity independent of shear rate. Whether you shear at 100 inverse seconds or 1,000 inverse seconds, you still get the same viscosity reading. However, if you shear at 10,000 inverse seconds and 20,000 inverse seconds, you're going to have two different viscosity values. And so finally out here at the infinite shear plateau, which is far, far, far from thermodynamic equilibrium, we now are in a regime where hydrodynamics dominate. And we have a new new plateau where we observe Newtonian-like behavior. And so lastly, just want to go over some viscosity scaling. This will be important later. It's really important when you're analyzing your data. It can help you compare differences more easily, even when you have different zero shear plateaus. And like I mentioned, it will make more sense in a couple slides. So, so starting broadly on your measurement plan isn't limited to shear rates. You can start broadly by measuring different temperatures as well and different formulations. And so over here on the left, we have phosphate buffer with 150 millimolar sodium chloride, and this protein model, bovine gamma globulin at 250 mg per mil. We have our viscosity here and the shear rates here. And we tested on, and as you can see, at different temperatures, we have very different zero shear plateau readings. So at 37 C, we're close to 15 centipoise. At 25, we're at 35. At 18, we're at 55. And at 10 degrees Celsius, we're almost at 95 centipoise, or millipascal seconds. But over here on the right, with a different buffer, phosphate buffered saline, with two different excipients. This is the same data that I showed 2 slides ago. Again, at 25 degrees Celsius, we have a zero shear plateau reading at 44 centipoise and a zero shear plateau reading of 38 centipoise for the formulation with arginine. And this is all at 25 C, and we have 3 different formulations, and we have 3 different shear plateaus, which goes to show you that your excipients matter and can wildly change your viscosity value. And you won't be able to, you wouldn't be able to characterize that if you only picked one number or one formulation and just kind of went with it and then ask questions later. Again, if you start broadly, you can kind of get a feel for how your formulation behaves. You'll be able to understand, oh, maybe this is why my formulation behaved poorly under a certain circumstance versus another. With that being said, this is kind of hard to read. So is there a way for us to be able to like compare these more clearly? And that we can with scaling. So that scaling that I showed before, which I neglected to put the equation on there, but I'll go back. So here we can equate the infinite shear plateau to the viscosity of the solvent or buffer. And then this is the zero shear plateau, and this is again the infinite shear plateau, and then this is our viscosity at varying shear rates. So if we scale our data by this factor, we can then collapse everything into one chart, and now it's really, really easy to compare our different formulations. So we can actually predict where the onset, or at least observe the onset of shear thinning more clearly when our data is presented in this way. So over here we can see as we cool our formulation down, the onset of shear thinning occurs at smaller and smaller shear rates. And then with our arginine formulation versus no arginine formulation, incorporating arginine delays the onset of shear thinning to higher shear rates than the formulation without shear thinning. And this would be a lot harder to see and a lot harder to internalize and rationalize if we didn't scale our data. But what does this all mean? So why does this shift occur? So we can ask our questions, well, does cooling our system down affect the size of our clusters that form? Or as we know, the larger something is, the slower it diffuses. So diffusion is a really important factor with viscosity, as in the Stokes-Einstein relation shown here. It's one of the parameters that controls diffusivity. So maybe that's a reason, but we don't know unless we figure out how we can relate size to diffusion. And so with that, there's this rheological parameter called the Peclet number, which is the ratio of basically diffusion and shear rate and size. And so Peclet number is basically the size of our or the volume that our particles take up times the shear rate times viscosity divided by kBT. And so we can use this to estimate the size of our particles. And so I guess one last thing before I move on. One reason why the onset of shear thinning occurs at lower shear rates at lower temperatures, the slower the diffusion, the more easily it is for hydrodynamic forces to overcome thermodynamic forces. And so, and that may be completely independent of size. But what we can do is use this Peclet number to calculate the size, and then we'll have our answer. So here we have this master curve, and I'll walk you through it very slowly. So here we have our scaling parameter, the same scaling parameter from the previous slides on the x-axis, or on the y-axis. And then on the x-axis, we have our Peclet number. And so again, we can think of it as the point where, or the ratio between hydrodynamic forces and thermodynamic forces. So if the onset of shear thinning is to transition from where thermodynamic forces dominate to where hydrodynamic forces dominate, then the critical shear rate would be where the Peclet number would be equal to 1. So where these two, both thermodynamic energy and hydrodynamic energy are equal to each other. And so we can then use this to determine the size of our or at least the volume of our particles in solution. And you can kind of see that if Peclet number is less than 1, that means KT is larger, or thermodynamic energy is larger than hydrodynamic energy. But if hydrodynamic energy is higher than thermodynamic energy, then Peclet number is greater than 1. So it helps conceptualize everything. And so we also know that with bovine gamma globulin, the hydrodynamic radius is 5 nanometers. The radius of gyration of a monomer is about 5.3 nanometers. And that the radius of gyration of a dimer, of a pure dimer, is 7.6 nanometers. So if we look and compare, all the temperatures and all the arginine or the formulation sizes of our proteins in solution, we find that all the temperature formulation, or all the different temperatures, the protein is the same size, approximately. Basically, all the proteins in solution, or the average volume that these, or the average radius of the proteins in solution in this formulation are about 10 nanometers. But if we look at the PBS formulation, we see that without arginine, the size of our proteins in solution, the average radius is about 9 nanometers. And then with arginine at 250 millimolar, we have 8 nanometers. And so we see that there's no significant change in interactions and clustering if we change temperature in our formulation, or our first formulation. However, we do see that this change in viscosity by arginine is driven by a reduced effective cluster size, which is reducing by the arginine, which is reducing the interaction. So it supports the idea of reversible cluster formation, changing or impacting viscosity of our protein formulations. And so this kind of shows that we went really broad. We started with just a simple shear rate sweep, and then also a temperature sweep thrown in, and then some buffer changing as well. And then we distilled it all and got really, really specific, used some creative data analysis to extract some really important information from our formulations. And so just to highlight further that here we have 10 nanometers, 9 and 8 nanometers, and these are all at the same temperature. The only difference is the formulations that we use. So again, showing how powerful the tool viscosity is for helping guide your formulation process. So if you are interested in reducing your viscosity and you have a protein formulation and you have excess arginine on hand, this may be a good way to A, show that it works, and B, say, hey, we need to use arginine in all of our formulations moving forward, if that's something that you're working on discussing with your teams in your different departments. And so with that, I'll go on to more other broad applications of viscosity. So for instance, sample differentiation. And again, I like to explore broad range so I can see what exactly is going on, and then narrow the range later. And a narrow range may be important for you in your specific applications. So on the left here, I have data of different maple syrups. So I have natural maple syrup here in green, and then pancake syrup, which contains some xanthan gum, that polymer that we know shear thins and follows power law behavior. And so just to go through some example of like why going broad helps, we go broad and we find, oh wow, our real natural maple syrup its viscosity is largely independent of shear rate. It's essentially a Newtonian fluid, but this manufactured pancake syrup is dramatically shear thinning. And so if we are trying to replicate the behavior of natural maple syrup for the customer, we need to think about the context at which the customer is going to be using this maple syrup. And so I would argue that most customers would be using very low shear rates to slowly get the maple syrup out of the bottle, to slowly drizzle it on their pancakes. So at low shear rates under 100 inverse seconds, this manufactured maple syrup is almost exactly the same viscosity as natural maple syrup. So the customer wouldn't be able to tell the difference. But I could foresee that you're at a manufacturing plant and you're trying to increase your volume, try to get product out, try to fill it as quickly as possible, and you're going to be operating in a high shear environment. And lo and behold, when you're shearing the pancake syrup at high shear rates, you're really reducing the viscosity, which is going to reduce the energy it takes to quickly process all the fluid flowing around the different pipes in your processing plant. But your natural maple syrup is largely going to be consistent. Its viscosity doesn't really change all that much across this wide shear rate range. So it may not be an ideal candidate for processing, whereas your pancake syrup has the advantage. So we characterized it first, went broad, and figured out, oh, this is really useful that we understand how these different fluids behave with each other. And now later we can go and decide, okay, for QC purposes, we're going to shear at 80 inverse seconds and use that as like a test to see, are we replicating natural maple syrup? And then while we're when we're coming up with a new pancake syrup formulation, but then when we're about to ship it off to the pilot plant or to manufacturing, we're going to test really quickly at 2,000 inverse seconds or 20,000 or whatever your shear rate you're going to be exposing them to during processing is going to be. We're going to measure the viscosity there and check and see if things are meeting our QC purposes. And then that's not limited to the food industry. Over here we have hydroxypropyl guar and sodium hyaluronate data, which in this example are used for eye drops, but we can use these for cosmetic serums as well. And so again, maybe the customer, at least with cosmetics, I don't know about eye drops, but in cosmetics, the more viscous something is, the more expensive it feels. So, and again, customers are not going to be shearing their material as dramatically as we are when we're processing and manufacturing our formulations. So maybe what we want is something that's easy to manufacture but feels luxurious and hands to the customer. So again, over here at a low shear rate, we have a noticeable difference in viscosity, but at the high shear rate, there is no difference. So these are two ideal candidates, or this is two ideal candidates for processing, but it also kind of helps us understand, oh, well, if we want something that feels luxurious, we'll go with the hydroxypropyl guar, or if we want something that, at least with eye drops, if I'm going to drop something in my eye, I don't really think I want anything thick in my eye, so maybe I'll go with the sodium hyaluronate formulation. So again, sample differentiation part two. So again, I'm going to piggyback something off from the cosmetics industry. So we have 3 different serums, and these are marketed as serums. One that was primarily made of simple oils, and then 2 that were made with different polymers, including hydroxypropyl and then sodium hyaluronate, and even xanthan gum. And again, the ones that contain these millions of Dalton's polymers behave like power law fluids, but the one serum that behaved Newtonian across all the shear rates that we tested had no polymers in it. So again, we can kind of see which ingredients are being used just based on the rheological behavior. And again, started off broadly to differentiate between the 3 different serums, because to the naked eye, they looked basically the same. But then we can figure out at specific shear rates really interesting properties about each of them. So here, the Revitalift and the Josie Maran behave very similarly at low shear rate, while this Prism serum was much lower in viscosity than the other 2 at low shear rate. And then even at high shear rates, the Josie Maran was pretty high in viscosity, while the other 2 were much lower in viscosity and even started to approach each other in viscosity at the highest shear rates. So again, starting broad and getting more specific. And so finally, with these specific with this specific data, which is shear rate sweeps of different milk and milk-like beverages, that's a really hot market nowadays. Milk-like beverages, which I would believe most people want milk that tastes or at least feels like they're drinking milk, but may not be milk. So having similar viscosity would be really, really important. So we have whole milk, skim milk, you have unsweetened almond beverage, and coconut milk, and an oat beverage. And we can see that most of them all replicate whole milk and skim milk pretty well, but the oat beverage does not. And that could be for a number of factors. One, oat beverage is primarily used as a coffee creamer. So like having something thicker to begin with to then dilute into coffee makes sense. But also there could be something within the oat itself, some kind of a protein or polysaccharide that really thickens the solution formulation. And you may be able to tease out exactly what part of that that formulation is causing or contributing to that viscosity. So maybe if you wanted an oat beverage that behaved more like whole milk, you would be able to figure out, okay, which of the components of this oat beverage is contributing to this viscosity increase, and is it possible for me to remove that from the final formulation and see if it replicates cow's milk more closely. So again, these are all like hypotheticals that you can use to guide your formulation process. You measure your material and kind of get a handle on it, figure out how it behaves over a broad range of environments, and then get specific and figure out, oh, okay, so this is how I'm going to alter my formulation moving forward. Or maybe I have this question, what's contributing to this discrepancy? Everything else seems to collapse onto one group. Why is this one so different? So again, viscosity measurements, rheology measurements are iterative. They are really fun for people who like to ask a lot of questions, who like to get their hands dirty and tinker. And I think I specifically, and also I think everyone at RheoSense agrees that it's fun to get in the lab and mess around and figure out some things and learn about your formulations. And so one final thing is using viscosity to characterize or get a handle on temperature sensitive polymeric excipients. So there's these poloxamers out there, these tri-block copolymers with 2 hydrophilic ends and then a central hydrophobic block that can change. They can dramatically change their rheological properties as they are heated and cooled. And in this specific instance, the poloxamer was really chosen to be used as a way to control the release of a drug that was loaded within the formulation. So the idea was that at body temperature, the poloxamer formulation would be really viscous, and so the drug candidate that was in solution with this poloxamer would slowly diffuse from the injection site. But there are other ways and other applications to use this poloxamer as well. And so with that, we've looked at two different poloxamers, this P188 and P407, both suspended in distilled water. And so just based on reading the instructions, you may have had an idea, okay, poloxamer P188 has a ratio of hydrophilic components to hydrophobic components 3:1, whereas poloxamer 407, this ratio is more 1.8. That seems like it's hard to control. I would actually prefer to use poloxamer 188 as my poloxamer of choice for the specific application. Based on this ratio, I feel, and I'm being hypothetical here, I feel like that's the one to go with. So you mix them both up together, but you want to do your due diligence, so you get both. So you mix them together, and then you perform a shear rate sweep or a temperature sweep, and come to find that actually the 407 thickens to its maximum viscosity at around body temperature, and the P188 thickens way over here at like almost 70 degrees Celsius. So that's not going to work. But if you only looked at, say, 25 degrees Celsius, you would have gotten a completely different answer. So going as broadly as possible actually kind of helps you figure out what exactly is going on here. And then additionally, we come to find that it requires less material in the case of P407 to cause a dramatic increase in viscosity at the appropriate temperature than it does with the P188. So you get to use less material, so you get more bang for your buck, and it goes over the temperature range that you want. And again, this came from going broad first and then narrowing it down to your specific needs. And so what we also, since we're just interested in how this behaves, this poloxamer behaves, we notice that it's not simple Arrhenius behavior. So in terms of the increasing temperature usually indicates a decrease in viscosity and a predicted path, and it knows the Arrhenius behavior. So this indicates that these poloxamers form complex and reversible microstructure, because we can go forward, we can go reverse, we can mix and match, and we still get very similar viscosity readings. And we also determined that this is really sensitive to concentration, as we can see here, going 13 to 15% weight percent. This is weight percent. It has a dramatic increase in the relative viscosity of our formulation. But we also know that's dependent on the poloxamer type and the ratio of hydrophilic and hydrophobic components. And then one last thing that we determined with our system is that we can detect phase boundaries here. So we know that we're going from a fluid phase to a gel phase between 30 and 45 degrees Celsius in the P407. And in the case of the P188, it's actually a little bit, I would say, a little broader, 50 to 70 approximately. And so again, to reiterate everything, start broad and then get specific. Don't let preconceived ideas about how your formulation is supposed to behave restrict you. So, here we can see that, at least with our platform, we can see that these poloxamer solutions at these mid temperatures around 40 degrees Celsius have some yield stress like behavior. And we can see that through what we call the transient curve here at RheoSense, or this curve of shear stress as a function of time. Now, as much as easy and convenient as this would be, we can't instantly induce a flow in our chamber. We can't suddenly go from no flow to infinite flow at the drop of a hat. So what happens is we induce flow and we slowly, over a period of seconds, ramp up to a steady state or steady shear environment. So we call this, and we track this in the software of our instruments. And so we can see, okay, we started the flow, it increases in shear stress and it reaches a plateau, and then we average over this region. So that when we say transient curve, we're talking about this. So in a transient curve where we have fluid flow, it goes from 0, transitions, and it goes to steady state, and it plateaus off. We see this at 30 degrees Celsius. We see this at 50 degrees Celsius. However, with a yielding material, we can see, in fact, that we see it goes from 0 and it starts increasing, and it increases in shear stress, but it doesn't plateau. What happens is it drops and then it plateaus. And this kind of behavior we see over and over and over again in materials that do yield. Now, we would like to be able to calculate the yield stress, but we can't currently do that with VROC technology. However, we can determine, oh, our system is, or our material is yielding. We can do that based on the shape of this transient curve. And we can use this to determine whether or not the material is yielding. We can determine if we're in a gel phase, or we're in our materials gel phase. So we can use this to kind of get an idea of how our material is behaving, but we can't get specific numbers just quite yet. And so here, again, trying to get a little more specific. So we picked, in this hypothetical experiment, 14 weight percent P407 as our ideal formulation. But now we want to characterize how it behaves at these different points, these different temperature points, getting specific. So we picked 20, 25, 30, 45, and 70 degrees Celsius. And what we find is we go from a Newtonian fluid at 20 degrees Celsius to largely non-Newtonian fluid and non-Newtonian behavior over the shear rate range that we've tested, from basically 25 degrees Celsius to 45 degrees Celsius. But then at 70 degrees, it goes back to Newtonian-like behavior and reduces in viscosity back down, very similar to what it was like at 20 degrees Celsius. And so this, again, we get a better idea how our formulation is behaving. Now, we can see, like, oh, maybe if we were developing this, for drug delivery applications, we could then say, okay, well, if we're having a protein-based therapeutic, we definitely don't want to heat it up to 70 degrees Celsius. And room temperature behaves weird, it behaves non-Newtonian, something we can't control. But lo and behold, if we cool our system down to 20 C, which isn't going to damage our protein, we can process this poloxamer formulation really easily. So this helps us understand what we can do from post-formulation development stage and trying to get up to pilot plant and scaling up our formulation process. So again, starting broadly and then getting narrow kind of shows us what gives us a better idea how our formulation behaves, but also helps us make important decisions later down the line. And so with that, I would like to just say that, rheological measurements are iterative. If you ask good questions at the beginning of your experiment or beginning of your project, it can lead to good experiments later. And to let the data guide you and to make educated guesses on what experiments to run and dive in. I want to reiterate that rheology is a broad field that's applicable to many industries and applications, as we saw here today, and that you can always contact us with questions. We're here to help you develop your techniques. And again, thank you so much for attending. the first ever Viscosity Summit. And with that, I think I have a few minutes to go over a couple questions.
Thanks so much, Dr. Imam. That was awesome. So you are right. We do have quite a few questions for you. And so I'm just going to dive in. The first is we have 2 questions, and so I'll just give them to you one at a time. So what are some of the adopted strategies utilized to reduce viscosity for liquid formulations besides concentration management and reformulation strategies?
Besides concentration and reformulation strategies. So it's all related to the microstructure. So of your system. So you can either, I guess, figure out where you can, if you could somehow operate where, like, let's just say you have a solution that is non-Newtonian and it shear thins over the range that the shear rate that you are going to be using in your application. That would be one way to be able to modulate the viscosity, I guess, without changing the formulation or the concentration. But it's not really well controlled because whether or not it shear thins over that range is kind of dependent upon the structure of the fluid within, which changes if you change the formulation or the concentration of your active component. So I guess there's no really great way to change the viscosity without changing the formulation or concentration, but you can change the temperature. You basically limited to changing the temperature or changing the shear rate if you're working with a non-Newtonian fluid.
Thank you. So a follow-up question or second question to that is, what is the recommended range for viscosity for high concentration liquid parenterals in pre-filled syringes, auto-injectors, and other self-administration devices?
So if I recall earlier today, Bart Deer mentioned that the hard limit in a lot of industry is 20 centipoise. I would say that I'm not as familiar with that as he is. However, what I would do is figure out what the injection force for your specific application is, and then make your decision based on that. And your injection force is dependent upon your viscosity and your shear rate and the dimensions of whatever syringe you're going to use. And so if, for instance, you set up like a parameter, like let's say 10 newtons of force. 10 newtons of force is my cutoff. Is there a way for me to develop a syringe that can deliver my product in under 10 newtons of force? And I can calculate that knowing the viscosity of my formulation, and then I can, with my injector, I can control the shear rate, and so I can predict what formulation is going to work, and with that specific application. And we here at RheoSense have quite a few application notes that kind of discuss how to calculate, or at least estimate, the injection force of our formulation to make that decision. So I wish I had a better answer, but that's that area is pretty murky because it's really dependent on formulation and like what your injection capabilities are.
So something you may know a little bit more about. Can we get zero shear viscosity using VROC instruments? And what is the minimum shear rate? Sorry, the two-parter.
I said yes all the time. So zero shear rate, like the zero shear plateau is essentially where your formulation behaves like a Newtonian fluid, where it's shear independent. So let's just say you run a shear rate sweep from 100 inverse seconds to 1,000 inverse seconds. If your viscosity remains constant over that range, and your or that range of shear rates, and you're not working with a like humongously long polymer, then you are on the zero shear plateau. So any of those shear rates would give you your zero shear rate, your zero shear viscosity. But if we're trying to go as low as possible on VROC technology, on the Initium we can go to 40 inverse seconds. Again, it depends on the viscosity of your sample, and then on the microvisc and MVROC, we can get to, I believe, below 1 inverse second. So if you're trying to go really, 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 really low, we can do that. But again, that's kind of sample dependent.
And this is less of a question, but just want to make sure we address it while everyone's still on. It looks like something got cut off at the bottom of your scaled viscosity versus master curve screen. Can we just share that again to see what the bottom looks like?
Let's see.
There we go. Yeah, it looks like I can see it. Is
it this one, or is it two slides behind?
I can, whatever you're showing right now is cut off, so it may be, but just your asterisks at the bottom, you can't.
Oh, so this was the citation for these numbers here.
Oh, perfect.
So, I can type it.
Maybe we can just drop it in the chat. So
yeah, we can drop it in the chat.
Anyone who wants to see the citation can. So another question, what is the representative shear rate to measure the viscosity for formulation that undergoes nebulization through a vibrating mesh nebulization at 128 kilohertz?
So can you repeat the question?
Yes, so what is the representative shear rate to measure the viscosity for formulation that undergoes nebulization through a vibrating mesh nebulization at 128 kilohertz?
I don't know that off the top of my head. Since it's nebulizing, I'm going to assume it's pretty high shear rate, but I'm sure there's in the rheology literature, I can pull out an equation for you to calculate that number out. So let's save that question, and then we'll go, Stacy and I will go and calculate that out and email it to the question asker.
Perfect. So we will send out an answer for that question to get the data. And can we measure viscosity versus shear rate curve for highly viscous fluids? So an example, tomato ketchup, using the VROC.
Yes. So we can measure those in VROC, but the caveat here is we have a limit since we use microfluidic chip. We do have a particle size limit. So as long as your particle size doesn't exceed 10% of the channel depth, then yes, we can measure those materials with VROC technology. So for instance, if you have a 50 micrometer depth channel, then your size cutoff is for your particles in solution is 5 microns. But if you use a 200 or a 300 micron channel, then your cutoff for your particles in solution are 20 microns and 30 microns respectively.
Perfect. And just one question I'm going to answer really quickly. We are going to be sending out recordings of all of our presentations for today to anyone who registered and all of our attendees. So his presentation, Zach's presentation, is going to be available once our recordings are done, in case anybody wants to go back through and see any of the slides he shared, you will be able to. And so another question for Zach, we've got a couple more coming in, and I know we're right at the end, but let's just get to these last three. What is the highest viscosity that can be measured inside VROC?
So the highest viscosity I've measured personally is 1,000 centipoise, but I do know that we have measured much higher than that, but I'd have to ask around, see.
I got to mention that someone's gone up to 8,000.
8,000, okay. I knew it wasn't 10, but yeah, okay. 8,000 is the maximum that we've done here at RheoSense.
And have you ever put cells through the VROC?
I haven't personally put cells through the VROC. I know we've tested blood before, like whole blood. So, but I've never personally put cells through VROC.
And the last question we have on here, how do you verify flow is laminar at high shear?
So we calculate the Reynolds number, and so so I'm not off the top of my head. I have to go consult with my notes, but our chips are small enough and our flow rates are small enough that we do not enter a regime where turbulent flow would be a problem in VROC. The only exception is our extensional chips, and specifically our extensional E chips. I believe there is the possibility for turbulent flow. But basically, when you have a Reynolds number of, I don't know what the cutoff is off the top of my head, but all of our, if you exceed this specific Reynolds number cutoff, that's where you enter turbulent flow, and all of our instruments, with the exception of that one, over all the flow rates that we can possibly test are all under that Reynolds number. So the turbulent flow isn't an issue with our technology.
I got another internal ping that we've tested cannabis oil, which is over 100,000 centipoise. So there's been a test at least. Well, I just want to thank everyone for attending, and Dr. Imam, thank you so much for your time and for this wonderful presentation. It was, I think, a really perfect tie-in to all of our presenters that we've had today, and now that we are at the end, I do want to thank all of our presenters, and I want to thank everyone who attended. And before we close out for the day, I just want to again remind everyone there are recordings of all of our sessions from today, and they will be shared a week after the event concludes. So we'll be sharing them out next week once the recordings are processed, and all of our attendees and registrants will get an email notifying you of that. And we'll also have it on our website so that for anyone who you may know who'd be interested that would like a link, we can share that as well. So be checking our site. And again, we encourage you to follow us on social media because we do share all of this on social as well. So if you follow us on LinkedIn, Twitter, or Facebook, we'll be certain to share the recording links with you there as well. So we just want to thank you all for joining us for the first ever Virtual Viscosity Summit. I hope it was a great start to your 2021. We enjoyed you all joining us and hope you enjoy the rest of your afternoon and evening. Thank you again, Dr. Imam.
Thank you.